The birth of strange matter, those hypothetical building blocks of the cosmos, is no gentle affair. It demands an environment so profoundly unforgiving, so utterly alien to our everyday experience, that it borders on the fantastical. Imagine pressures so immense they would crush a black hole into oblivion, temperatures that dwarf the fiery heart of a star, and densities that defy comprehension. These are not conditions one stumbles upon in a laboratory. They are the exclusive domain of the universe's most cataclysmic events. The prime suspects in the creation of these exotic particles are none other than neutron stars, and the explosive demise of massive stars, supernovae. Neutron stars, themselves remnants of stellar collapse, are already the densest objects known, packed with neutrons under unimaginable pressure. It is within these celestial titans, particularly during their violent mergers, or when accreting matter from a companion star, that the sheer force might be sufficient to break down neutrons into their constituent quarks up, down, and crucially, strange quarks. If these quarks can then coalesce in the right proportions, forming a stable, strangelet, a new, potentially universe-altering substance could emerge. Supernovae, the spectacular death throes of stars many times more massive than our sun, offer another potent arena. The shockwaves and immense energy released during these explosions can momentarily create conditions akin to the primordial universe, a fleeting state known as the quark-gluon plasma. This plasma, a soup of unbound quarks and gluons, is theorized to be the very medium from which ordinary matter, and perhaps even strange matter, first coalesced after the Big Bang. Some cosmologists speculate that if the quark-gluon plasma generated in a supernova cools and compresses in a particular way, it could serve as a fertile ground for the spontaneous formation of strangelets, seeding the cosmos with these enigmatic particles. The theoretical underpinnings of strange matter formation are deeply rooted in the standard model of particle physics, specifically in the concept of quantum chromodynamics. QCD describes the strong nuclear force that binds quarks together. Within the extreme conditions of neutron stars and supernovae, it's hypothesized that the energy barrier to forming a stable configuration of up-down and strange quarks, known as a color superconductor, might be overcome. This stable state, or strange quark matter, is predicted to be more energetically favorable than ordinary nuclear matter under certain extreme pressures. If this hypothesis holds true, then even a tiny seed of strange matter could, in theory, convert ordinary matter it encounters into more strange matter, a process that has profound implications for the structure and evolution of neutron stars and potentially the very fabric of the universe. The quest to understand these cosmic crucibles, where matter is pushed to its absolute limits, is a journey into the heart of physics and the very origins of existence. Imagine, if you will, a state of matter so fundamentally alien that it challenges our very definition of existence. This isn't the familiar dance of protons and neutrons within atomic nuclei, but a far more primal, potent realm, strange matter. Here, the building blocks of reality, quarks, are not confined within their usual, tightly bound structures. Instead, in this hypothetical state of bulk matter, we find a teeming aggregation of up, down, and the enigmatic, strange quarks. These fundamental particles, imbued with an intrinsic property known as color charge, are not merely passive components, they are active participants in a grand, unseen choreography. The theoretical underpinning of this exotic state lies in the fascinating concept of the color superconductor. Within the extreme pressures and densities envisioned for strange matter, the strong nuclear force, mediated by particles called gluons, undergoes a radical transformation. Instead of individual quarks being bound, pairs of quarks can form a coherent quantum state, akin to superconductivity in ordinary matter where electrons flow without resistance. In this color superconductive phase, the strong force effectively becomes an attractive medium, allowing for a stable, bulk arrangement of quarks. This collective behavior, driven by the intricate interplay of color charges, is what bestows upon strange matter its potential for extraordinary stability. But why might this bizarre concoction be more stable than the nuclear matter that forms the core of our everyday universe? The answer, elegantly simple in its implication, lies in the very nature of the strange quark. Adding these third-generation quarks into the mix, alongside the more common up and down quarks, can lower the overall energy of the system. Think of it like a more efficient packing arrangement, The presence of strange quarks allows the quarks to exist in a more energetically favorable configuration. This reduction in energy, a fundamental driving force in the universe, suggests that if strange matter can indeed form, it might represent a truly ground state for matter under extreme conditions. Its existence could redefine our understanding of neutron stars, transforming them from mere remnants of stellar collapse into cosmic laboratories, showcasing the ultimate resilience and potential for novel forms of matter that the universe can conjure. The implications ripple outwards, hinting at a universe far stranger and more magnificent than we currently comprehend. Imagine, if you will, a universe where the very building blocks of reality, the fundamental constituents of matter, transcend their usual roles. We speak of quarks, those elusive entities that, bound together by the strong nuclear force, form protons and neutrons. But what if, under conditions of unimaginable density and pressure, such as within the heart of a neutron star, or in the nascent moments of the Big Bang, quarks could assemble in configurations far beyond our current understanding? This is the realm of strange matter, a hypothetical state of matter composed not just of up and down quarks, but also of strange quarks. And within this alien landscape, we dare to ponder the existence of dreaming molecules. These are not molecules as we know them, forged from atoms held together by electron clouds. Instead, think of them as intricate, self-sustaining structures where clusters of quarks, perhaps in a stable, strangelet configuration, interact and bind through the very force that holds them captive. The dreaming aspect arises from the sheer exoticism of their potential existence and the profound questions they raise about the fundamental nature of organization and consciousness. Could such a tightly bound, quantum-bound entity, existing at the very edge of nuclear stability, exhibit emergent properties that we might metaphorically, or perhaps even literally, describe as a form of rudimentary dreaming? It's a leap of imagination, certainly, but one grounded in the extraordinary possibilities offered by the physics of extreme environments. Central to this speculative dance is the phenomenon of quantum entanglement. If these strange matter molecules were to form, entanglement would likely be a pervasive, intrinsic characteristic. Imagine a scenario where multiple strangelets, or even constituent quarks within a larger strange matter condensate, become inextricably linked. A change in the quantum state of one would instantaneously influence the state of others, regardless of the distance separating them. This would not be a mere chemical bond, but a deep, interwoven fabric of quantum correlation. These dreaming molecules might, in essence, be perpetually entangled entities, their very existence a testament to the universe's capacity for interconnectedness at the most fundamental level. Their internal dreams, if they exist, could be shared across their entangled brethren, creating a localized network of quantum information processing that defies our macroscopic intuition. The primary hurdle in exploring this fascinating frontier is, undeniably, observation and verification. Strange matter, even in its less speculative forms, is exceedingly difficult to detect. Its existence is largely inferred from theoretical models and potential astrophysical signatures, such as anomalous cosmic ray events or the precise mass-radius relationship of neutron stars. Detecting a dreaming molecule would require a paradigm shift in our observational capabilities. We would need instruments capable of probing the interior of neutron stars with unprecedented precision, or perhaps identifying unique decay signatures or energy emissions that are characteristic of these hypothetical structures. Furthermore, how would we even begin to identify an emergent property, like dreaming in such an alien context? Our current scientific toolkit is largely designed to observe and measure phenomena within the familiar framework of atomic and subatomic interactions. Distinguishing the subtle quantum correlations of entangled strangelets from the background noise of cosmic phenomena would be a monumental task, demanding innovative experimental designs and perhaps entirely new theoretical frameworks for interpreting data. The universe, it seems, guards its deepest secrets with profound complexity, and the dreaming molecules of strange matter, if they exist, represent some of its most enigmatic enigmas. Imagine, if you will, a realm beyond the familiar dance of electrons and protons, a place where the very fabric of matter is rewoven by the relentless grip of the strong nuclear force. We stand on the precipice of hypothesizing entirely novel bonding mechanisms for what we tentatively call strange matter molecules. Unlike the electrostatic whispers that bind our everyday atoms, these hypothetical structures would be forged in the inferno of the strong force, a cosmic glue of unimaginable power. Here, quarks up, down, and the elusive strange quark would not merely exist in fleeting moments within nucleons but would coalesce, held in an almost eternal embrace. The strong nuclear force, that titanic power responsible for holding atomic nuclei together against the immense electrostatic repulsion of protons, would be the architect of these strange molecular configurations. It's not just about packing more quarks together, it's about how they arrange themselves, forming stable clusters, perhaps even crystalline lattices of pure strangeness. Think of it as a hyper-dense, multi-dimensional crystal, where the bonds are not electron orbitals but direct, powerful interactions between the fundamental constituents of matter. The sheer density and energy within these hypothetical structures would dwarf anything we observe in conventional chemistry. What would such an embrace portend for the properties of matter? The potential for unique chemical properties and interactions is staggering. If strangelets, these hypothesized building blocks of strange matter, could indeed form larger, stable molecules, they might exhibit an entirely new form of chemistry. Instead of covalent or ionic bonds, we might witness interactions dictated by the specific arrangement and flavor composition of the quarks. Could these structures catalyze reactions in ways we can't even fathom? Might they possess incredible tensile strength, resisting forces that would shatter ordinary matter? Perhaps they could store and release energy with unprecedented efficiency, acting as cosmic batteries. Exploring these possibilities requires us to cast aside our ingrained chemical intuitions and embrace a new paradigm, one where the strong force dictates the molecular destiny. It's a journey into the heart of matter's most fundamental interactions, a quest to understand the universe's most extreme and potentially most powerful molecular creations. This is not just about new elements. It's about a fundamentally new way for matter to assemble itself, driven by forces we are only beginning to truly appreciate in their most potent manifestations. The universe, in its boundless audacity, does not limit its creations to the familiar dance of protons and neutrons. Within the crushing embrace of neutron stars, under pressures that would pulverize any terrestrial substance, a profound metamorphosis can occur. Should the delicate balance of forces tip, the very nuclei of atoms could shatter, their constituent quarks up and down spilling forth, not to scatter, but to coalesce into a new, stable entity, strange matter. Imagine, if you will, a sea of up-down and the enigmatic strange quarks, bound together not by the ephemeral strong force of individual nucleons, but by a shared, profound interaction. This is the realm of strangelets, hypothetical particles composed of roughly equal numbers of up, down, and strange quarks. While our current understanding suggests they would be incredibly dense, potentially far exceeding that of nuclear matter, their existence and properties remain a tantalizing frontier of theoretical physics. The implications of such exotic matter, if it indeed exists in significant quantities, are staggering, particularly concerning its gravitational influence. A sufficiently large concentration of strange matter, such as a neutron star entirely composed of it, a hypothetical, strange star, would exert a gravitational pull unlike any conventional star. Its density could be so immense that its surface gravity might be orders of magnitude greater than that of a typical neutron star. This extreme gravitational dominance could manifest in several observable ways, offering us a cosmic fingerprint to seek. One tantalizing observational signature could be found in the behavior of pulsars, those rapidly rotating neutron stars that emit beams of radiation. A pulsar situated within or near a region of dense strange matter might exhibit anomalous properties. Its spin rate could be influenced by the intense gravitational field, potentially leading to faster rotation or unusual variations in its pulse period. Furthermore, the very composition of the star could affect the magnetic fields responsible for the pulsar's emission, leading to peculiar radiation patterns or even a suppression of observable signals if the strange matter core significantly alters the star's structure and magnetosphere. Perhaps the most compelling, albeit challenging, avenue for detection lies in the realm of gravitational waves. As massive objects like neutron stars or black holes spiral towards each other and merge, They generate ripples in space-time that propagate across the cosmos. The gravitational waves emitted by the merger of two strange stars, or a strange star with a black hole, would likely possess distinct characteristics compared to those produced by conventional neutron-star mergers. These differences would stem from the unique mass, radius relationship and internal structure of strange matter. By meticulously analyzing the waveforms of detected gravitational waves, scientists could potentially discern the telltale signatures of these ultra-dense, exotic objects, offering direct evidence for the existence of strange matter. The question then arises, how do we distinguish these potential cosmic behemoths from other proposed constituents of the universe, most notably dark matter? Dark matter, the invisible scaffolding that shapes galaxies and large-scale structures, remains one of physics' greatest enigmas. While both strange matter and dark matter are theoretical constructs that elude direct visual observation, their proposed properties and interactions differ significantly. Dark matter is generally understood to interact weakly with ordinary matter and electromagnetic radiation, primarily through gravity. Its distribution is thought to be diffuse, forming halos around galaxies. In contrast, strange matter, if it exists as compact objects like strange stars, would be incredibly dense and gravitationally potent, capable of significantly warping spacetime in its immediate vicinity. Furthermore, if strange matter were to interact with ordinary matter in specific ways, for instance, through a hypothetical, strange quark catalysis, where ordinary matter hitting strange matter could convert into strange matter, these interactions would provide a stark contrast to the typically non-interactive nature of dark matter. Distinguishing between them would necessitate a multi-pronged observational approach, combining the study of stellar populations, gravitational wave astronomy, and perhaps even direct detection experiments if strange matter were to exist in a more dispersed form accessible to terrestrial detectors. The search for strange matter is, in essence, a quest to understand the universe's most extreme and potentially most powerful molecular creations. This is not just about new elements, it's about a fundamentally new way for matter to assemble itself, driven by forces we are only beginning to truly appreciate in their most potent manifestations. Imagine a universe where the very bedrock of existence, the familiar dance of protons and neutrons, could be fundamentally rewritten. We stand at the precipice of such a revelation, exploring the audacious concept of strange matter catalysis. This isn't merely about creating new elements, it's about a transformative process, a cosmic alchemy where ordinary matter, under specific, extreme conditions, might be tempted to shed its familiar guise and embrace the binding power of strangelets. Think of it as an infection of the nuclear world, where a single strangelet, a hypothetical cluster of up-down, and strange quarks, could act as a seed, converting surrounding nucleons into its own unique, incredibly dense form. The implications of such a phenomenon ripple through the grand tapestry of cosmic evolution, particularly in the dramatic lives and deaths of neutron stars. These stellar remnants, already the densest objects known, are the prime candidates for harboring and potentially propagating strange matter. If strange matter catalysis is indeed a reality, a neutron star could, over eons, gradually convert its entire mass into a stable, ultra-dense core of strange matter. This would profoundly alter our understanding of their internal structure, their magnetic fields, and even the explosive supernovae that mark their birth. Instead of a neutron star collapsing or bouncing back from gravity's crushing embrace, it might instead undergo a quiet, fundamental transformation, its dense neutronium heart surrendering to the allure of the strange. But the concept of strange matter catalysis doesn't stop at reshaping stellar corpses. It ventures into the realm of the truly cataclysmic, positing the theoretical possibility of stable, self-sustaining strange matter bombs. These aren't conventional explosions, they are envisioned as exotic objects, potentially small yet possessing unimaginable density and binding energy. Once initiated, a strangelet bomb could theoretically continue to convert ambient matter into more strange matter, propagating its unique state like a runaway chain reaction. The sheer energy released in such a conversion would dwarf anything we witness in typical nuclear processes. While purely theoretical at this stage, the idea compels us to consider the most extreme energy potentials inherent in the universe's fundamental building blocks, pushing the boundaries of what we deem possible in the cosmic arena. The universe, it seems, may harbor secrets of matter assembly far more profound and potent than we have dared to imagine. The staggering density of strange matter, a theoretical substance composed of up, down, and strange quarks bound together, presents a profound challenge to our current understanding of gravity and the very fabric of the universe. Imagine a substance so incredibly compact that a mere teaspoonful could outweigh Mount Everest. Such extreme concentration of mass and energy, far surpassing that of neutron stars or even black holes in their conventional understanding, could exert an influence on space-time that ripples outwards in ways we are only beginning to contemplate. General relativity, our most robust framework for describing gravity, predicts that mass and energy warp space-time, causing the curvature we perceive as gravitational pull. However, the unique properties of strange matter, particularly its potential to exist in a stable, super-dense state, suggest that this warping might not be a simple, smooth distortion. Instead, we might witness exotic gravitational phenomena that defy the elegant, yet ultimately incomplete, predictions of Einstein's equations. Think of it not as a gentle dimple on a stretched rubber sheet, but as a violent, localized tear or a complex, multi-dimensional fold. The immense pressure and unique quark composition of strange matter could lead to gravitational effects that are highly anisotropic, meaning they vary dramatically depending on the direction of observation. This could manifest as gravitational fields that possess an intrinsic spin or a peculiar asymmetry, unlike the spherically symmetric gravitational pull we observe from ordinary objects. Furthermore, the very existence of stable strangelets, if they do exist, implies that the strong nuclear force, under these extreme conditions, can overcome the electromagnetic repulsion that normally keeps atomic nuclei apart. This fundamental difference in how matter is organized could translate into equally fundamental differences in how it interacts with spacetime. The implications for astrophysics are staggering. We might be searching for gravitational signatures that are not merely stronger, but qualitatively different from those predicted by standard models. This could include localized distortions in spacetime that are not associated with the typical presence of massive objects like stars or galaxies, but rather with the subtle, yet powerful, influence of these exotic matter configurations. Imagine regions of space where light bends in unexpected ways, where orbits of celestial bodies are subtly perturbed by an unseen, non-standard gravitational source, or where gravitational waves exhibit unique patterns that betray the presence of strange matter. The search for these localized space-time anomalies becomes a quest for the universe's hidden architecture, for the whispers of matter so dense and so alien that it sculpts the very canvas upon which reality is painted. It requires us to look beyond the familiar gravitational signatures and to develop new observational techniques and theoretical tools capable of detecting these subtle, yet potentially revolutionary, deviations from the norm. The universe, in its infinite complexity, may be orchestrating gravitational ballots with players we have yet to fully comprehend, and strange matter could be one of its most enigmatic performers. The very concept of dreaming molecules within the realm of strange matter conjures an astonishing vista of emergent complexity. Imagine these fundamental building blocks, not merely existing in isolation, but actively seeking each other, guided by forces we are only beginning to glimpse. Their aggregation into larger structures wouldn't be a chaotic jumble, but a meticulously orchestrated dance. We can speculate that their inherent properties, perhaps a subtle interplay of nuclear forces and residual electromagnetic charges, might lead to the formation of crystalline lattices or filamentary networks, akin to cosmic lace. The sheer density and unusual quantum mechanical properties of strange matter could dictate entirely novel modes of self-assembly, far removed from the familiar van der Waals forces that govern conventional molecular bonding. Crucial to this organizational ballot are the potent magnetic fields that permeate the cosmos. As strange matter, potentially born in the cataclysmic aftermath of neutron star mergers or within the hearts of hypernovae, is ejected into the interstellar medium, these pervasive magnetic fields would act as invisible shepherds. They could channel and concentrate these exotic particles, coaxing them into spiraling accretion disks around nascent stellar objects or even forming vast, diffuse clouds. These disks, already known for their role in planet formation, might instead become nurseries for colossal conglomerates of strange matter, their internal dynamics dictated by the unique equation of state of this peculiar substance. The accretion process itself, driven by gravity and amplified by magnetic field lines, could sculpt these entities into toroidal shapes, flattened disks, or even more complex, self-sustaining structures. This leads to the captivating question: do vast interstellar clouds, composed not of hydrogen and helium, but of these truly alien entities, drift through the cosmic expanse? If strange matter is indeed as stable as theoretical models suggest, then such nebulae are not just plausible, but perhaps even probable. These strange nebulae might appear as regions of unusual darkness, absorbing or scattering light in ways that defy conventional astrophysical explanations. Their gravitational influence would be disproportionately large for their apparent visibility, creating localized distortions in space-time that could be subtly detected by advanced gravitational wave observatories or through precise measurements of stellar orbits. The very composition of these potential clouds would be a subject of intense study, with their spectral signatures, if any, revealing a universe far richer and stranger than we currently perceive, a universe where the fundamental constituents of matter can dream and coalesce into forms beyond our wildest imaginings. The universe, in its infancy, was a crucible of unimaginable energy and density. In those fleeting moments after the Big Bang, when the very laws of physics were still being etched into existence, a radical transformation of matter may have occurred. It is within this primordial soup, a searing, expanding plasma of fundamental particles, that the seeds of strange matter might have been sown. Imagine, if you will, a cosmic dance of quarks and gluons, a chaotic ballet where, under conditions of extreme pressure and temperature, the ordinary quarks that form protons and neutrons could have rearranged themselves into a more stable, exotic configuration strangelets. These hypothetical droplets of strange matter, born from the universe's fiery genesis, could have been the silent, unassuming architects of the cosmos as we know it. The very early universe provides a fertile ground for the formation of strangelets. As the universe cooled and expanded, the conditions that favored their creation would have gradually faded. However, any strangelets that managed to coalesce during this epoch would have persisted, acting as enduring relics of this energetic infancy. Their survival hinges on their inherent stability. Unlike the fleeting existence of many exotic particles, strangelets, if they are indeed more stable than ordinary nuclear matter, would have endured the aeons, a constant presence in the cosmic tapestry. The implications of this early formation are profound. These primordial strangelets would not have merely been passive observers, they could have actively influenced the subsequent evolution of the universe. Consider how these ancient aggregates might have acted as gravitational anchors, drawing in ordinary matter and seeding the formation of early structures. As the universe continued to cool, ordinary matter would have clumped together, forming stars and galaxies. If strangelets were present, they could have served as the initial nuclei around which this matter coalesced, accelerating the process of structure formation and shaping the large-scale distribution of galaxies we observe today. The very distribution of matter, the cosmic web of filaments and voids, could bear the indelible fingerprints of these early strangelet seeds. Connecting these theoretical musings with current astronomical observations is a fascinating endeavor. While direct detection of primordial strangelets remains elusive, their indirect influence could be imprinted on the cosmic microwave background radiation. Subtle anisotropies in the CMB, the afterglow of the Big Bang, might reveal patterns that are best explained by the presence of a significant component of strange matter in the early universe. Furthermore, the observed abundance of light elements, forged in the Big Bang nucleosynthesis, could also be affected by the presence of strange matter, potentially requiring adjustments to our standard cosmological models. The search for evidence of primordial strangelets extends to the study of neutron stars. These incredibly dense remnants of stellar collapse are thought to be composed primarily of neutrons, but some theories propose that their cores might contain a significant fraction of strange matter, forming a strange star. If strange stars exist and are a common outcome of stellar evolution, it would lend substantial weight to the idea that strange matter is a fundamental constituent of the universe, with its origins tracing back to the Big Bang itself. The spectral signatures of these potential clouds, if any, would reveal a universe far richer and stranger than we currently perceive, a universe where the fundamental constituents of matter can dream and coalesce into forms beyond our wildest imaginings. The tantalizing possibility of strange matter, those hypothetical droplets of quark, gluon plasma stabilized by their own unique physics, ignites a fervent quest within the scientific community. Our current arsenal for its detection is a tapestry woven from both established techniques and ambitious proposals, each aiming to snag a glimpse of this elusive entity. Ground-based experiments, like those employing sophisticated particle detectors, meticulously sift through the cosmic deluge, seeking anomalies in the expected behavior of known particles. These instruments, often buried deep underground to shield them from the incessant chatter of background radiation, are akin to ancient alchemists patiently observing the subtle shifts in their crucibles, hoping for a sign of transmutation. The proposed methods paint an even more ambitious picture. Scientists are exploring the potential for strange matter to influence the very structure of neutron stars, those colossal remnants of stellar explosions. If a neutron star were to accrete strange matter, it might transform into a strange star, exhibiting distinct gravitational and thermal properties that could be discernible through advanced astronomical observations. Imagine a cosmic lighthouse, not merely signaling its presence with light, but subtly altering the fabric of spacetime itself, a gravitational whisper that only the most sensitive instruments can decipher. Furthermore, the theoretical interactions of strange matter with ordinary matter could, under specific circumstances, produce unique radiation signatures, veritable cosmic fingerprints waiting to be recognized. However, the path to confirmation is fraught with challenges, chief among them the daunting task of distinguishing the faint whispers of strange matter from the cacophony of background noise. The universe is a remarkably noisy place, awash in the energetic debris of countless cosmic events. Identifying a signal that is both rare and subtle requires an almost supernatural level of precision and a deep understanding of every potential source of interference. It's like trying to hear a single, perfectly tuned note played on a violin amidst the roar of 1,000 orchestras. This is where the mighty engines of particle accelerators and the vigilant eyes of cosmic ray observatories play their crucial roles. Particle accelerators, like gargantuan cosmic simulators, can recreate the extreme conditions thought to have prevailed in the early universe, allowing physicists to probe the fundamental interactions of matter in controlled environments. While direct creation of stable strange matter in accelerators remains a formidable hurdle, these facilities can generate and study the exotic particles that might serve as precursors or indicators. Cosmic ray observatories, on the other hand, act as our celestial sentinels, continuously monitoring the high-energy particles that bombard Earth from the far reaches of space. By analyzing the composition and trajectories of these incoming cosmic messengers, scientists can search for telltale signs of interactions with or origins from strange matter. It is a continuous, collaborative effort, a grand scientific detective story where every anomaly, every unexpected deviation, is a potential clue leading us closer to understanding the universe's most profound secrets. The quest to understand strange matter, this exotic state of nuclear matter, pushes the boundaries of our experimental capabilities, drawing us into the heart of simulated cosmic cataclysms. In the realm of high-energy physics, the creation of conditions that might coax ordinary quarks into the stable, bizarre configuration of strangelets is not a matter of chance, but a meticulously engineered endeavor. Laboratories around the world act as miniature cosmic crucibles, where atomic nuclei, stripped of their electrons and accelerated to near light speed, are hurled against each other with unimaginable force. These collisions, brief yet incredibly energetic, momentarily recreate the extreme densities and temperatures that prevailed in the universe's infancy mere microseconds after the Big Bang. It is within these fleeting moments, within the ephemeral fireball of colliding particles, that the fundamental forces of nature are laid bare, and the very building blocks of matter are tested in ways that nature itself rarely affords us. At the forefront of this exploration stand giants of experimental physics, the relativistic Heavy Ion Collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN. These colossal machines are not merely accelerators, They are sophisticated observatories designed to map the intricate phase diagram of nuclear matter. Much like meteorologists study atmospheric pressure and temperature to predict weather patterns, physicists use RHC and the LHC to probe the different states or phases that nuclear matter can exist in. From the familiar plasma of quarks and gluons, a state reminiscent of the very early universe, to the hypothetical but tantalizing realm where strange matter might emerge, these colliders allow us to chart the transitions and understand the fundamental forces that govern them. The collisions are meticulously controlled, with detectors of immense complexity capturing the debris of these interactions, searching for the subtle signatures that would indicate the formation of strangelets. Imagine a vast array of microscopic eyes, each trained to spot the faintest whisper of an anomalous event, a deviation from the expected, that could point towards the existence of this elusive substance. The lessons learned from decades of heavy, ion collisions have been profound, reshaping our understanding of the strong nuclear force and the nature of matter itself. We have moved beyond a simple picture of protons and neutrons as indivisible entities, recognizing them as complex arrangements of quarks and gluons. The quark-gluon plasma, once a theoretical construct, has been experimentally confirmed, exhibiting properties that are surprisingly fluid, like a far cry from the gas-like behavior initially predicted. Each collision, each analyzed event, contributes to a growing body of knowledge, refining our theoretical models and guiding future experimental strategies. The search for strange matter is a testament to this iterative process of discovery. We are not simply looking for a needle in a haystack, we are learning to build a better haystack, to create the conditions where the needle is more likely to appear, and to train our eyes to recognize its glint. The journey is arduous, marked by meticulous data analysis, theoretical refinement, and the constant challenge of pushing technological limits. Yet, the potential reward, the confirmation of strange matter's existence, and the unlocking of its secrets promises to revolutionize our understanding of the cosmos and our place within it. It is a journey that ignites curiosity, fosters collaboration, and drives the relentless human spirit of scientific inquiry, seeking to comprehend the deepest, most fundamental truths of reality. While the allure of strange matter as a cosmic sculptor is undeniable, its theoretical existence also casts a long shadow of profound, albeit speculative peril. Imagine, if you will, a universe inadvertently seeded with a single, stable crumb of strange matter. The very fabric of ordinary matter, the protons and neutrons that constitute everything we know and perceive, could be susceptible to conversion. Upon contact, the strangelets could act as a catalyst, initiating a terrifying chain reaction. The strong nuclear force, the glue holding atomic nuclei together, might be overwhelmed. Neutrons and protons encountering this alien configuration could be transmuted into a more stable, strange matter state. This isn't a slow erosion. Theoretical models suggest a rapid, almost instantaneous, conversion process. A single stray strangelet could, in principle, consume an entire star, then another, spreading like an unstoppable cosmic contagion. The implications are staggering, a universe not merely altered, but fundamentally rewritten, atom by atom, into a state utterly alien and potentially inimical to life as we understand it. However, it is crucial to ground these chilling visions in the current scientific landscape. The overwhelming consensus within the physics community is that such a cataclysmic scenario, while a fascinating theoretical construct, remains firmly in the realm of the highly improbable. Decades of cosmic ray observations, the continuous bombardment of Earth by high-energy particles from space, have provided no evidence for the existence of naturally occurring, stable strangelets that could trigger such a conversion. If stable strange matter were common in the universe, or if even small, naturally occurring samples possessed this destructive potential, we would likely have observed its effects already. The very absence of such observed phenomena lends considerable weight to the hypothesis that either stable strange matter does not exist, or if it does, it is exceedingly rare and inherently non-threatening in its natural state. Despite this scientific consensus, the concept of a gray goo scenario involving strange matter continues to capture the public imagination, often fueled by sensationalized accounts in popular media. This disconnect highlights a persistent challenge in communicating complex scientific concepts and their associated risks. while the theoretical possibility of a strange matter event serves as a potent thought experiment, underscoring the immense power and mystery of fundamental physics. It is vital to distinguish between theoretical exploration and imminent danger. Educational efforts must strive to convey not only the fascinating implications of exotic physics, but also the robust observational evidence and the rigorous scientific processes that inform our understanding of the universe's potential dangers, separating the realm of theoretical speculation from the practical realities of cosmic evolution and earthly safety. The universe, in its unfathomable expanse, frequently delivers surprises that challenge our fundamental understanding. Among the most compelling of these cosmic puzzles are the anomalies detected in the composition of high-energy particles that incessantly bombard our atmosphere, the cosmic rays. For decades, scientists have meticulously analyzed these celestial messengers, and in their intricate spectral signatures, a subtle discord has begun to emerge, hinting at the presence of something profoundly other. These are not merely the familiar protons and alpha particles we expect. Embedded within the flux are heavier, more exotic nuclei, their very existence a whisper from the void that could signify the touch of strange matter. The search for these elusive heavy, exotic nuclei in space is a testament to humanity's relentless curiosity and the sophisticated tools we've developed to probe the cosmos. Telescopes and detectors, both on Earth and in orbit, act as our eyes and ears, sifting through the torrent of cosmic radiation. They are designed to capture, identify, and measure the properties of these incoming particles with astonishing precision. What they are increasingly finding are patterns that deviate from the expected abundance of standard baryonic matter. Imagine sifting through a vast ocean of sand, expecting to find only quartz and feldspar, but instead discovering grains of an entirely unknown mineral, possessing a density and atomic structure that defy conventional explanation. This is the essence of the current investigation. Interpreting the spectrum of high-energy particles, reaching Earth is akin to deciphering an ancient, complex language spoken in the violent dialect of astrophysical phenomena. Each particle, with its unique energy, charge, and mass, carries a piece of information about its origin and journey through the cosmos. When we observe a surprising overabundance of certain heavy elements, or even the detection of particles with characteristics that don't fit neatly into the periodic table as we know it, it's a signal that demands rigorous scrutiny. These are not random fluctuations, they are potential fingerprints of processes and substances that lie beyond our current theoretical frameworks. Could these anomalies be the faint, yet undeniable, echoes of strange matter, perhaps in the form of strangelets, hypothetical compact lumps of quarks composed of up, down, and strange quarks? The theory suggests that if strange matter exists and is stable, it might be produced in cataclysmic events like neutron star mergers, or even in the early universe. If it were to form, these strangelets, potentially possessing a range of masses, could be ejected into interstellar space and eventually reach our solar system. Their interaction with regular matter could have unique characteristics, influencing the composition of cosmic rays we observe. The scientific community approaches these findings with a blend of excitement and caution. The implications of confirming the existence of strange matter are staggering, potentially rewriting our understanding of nuclear physics and the fundamental forces that govern the universe. However, the evidence is still being meticulously gathered and analyzed. Scientists are employing advanced computational models to simulate the formation and propagation of such exotic particles, comparing these theoretical predictions with the observational data. The challenge lies in distinguishing the signatures of strange matter from other, more conventional astrophysical explanations for observed anomalies. For instance, unusual distributions of heavy elements could also arise from novel nucleosynthesis processes in extreme stellar environments, or from the decay of hypothetical particles not yet accounted for in the standard model. The ongoing quest to understand these cosmic ray anomalies is a captivating journey into the unknown. It highlights the dynamic nature of scientific discovery, where persistent observation and rigorous analysis gradually peel back the layers of cosmic mystery. Whether these whispers from the void ultimately confirm the existence of strange matter or lead us to entirely new, unexpected physics, the pursuit itself is a profound exploration of the universe's deepest secrets, reminding us that the cosmos is a boundless canvas for phenomena that continue to ignite our imagination and expand the frontiers of human knowledge. The careful deciphering of these energetic visitors is not just an exercise in astrophysics, it's a critical step in charting the unseen territories of reality. The potential discovery of stable strange matter, a theoretical state of matter composed of up, down, and strange quarks, represents a paradigm shift of monumental proportions. Its implications stretch far beyond the realm of theoretical physics, touching upon the very fabric of our cosmic understanding. If confirmed, stable strange matter would not merely be another exotic particle or phenomenon, it would be a fundamental building block, a new cornerstone upon which our comprehension of the universe is built. Imagine the profound impact on fundamental physics. Our current models, from the standard model of particle physics to the intricacies of nuclear forces, are predicated on the known states of matter. The existence of stable strange matter would necessitate a radical re-evaluation, a complete overhaul of our theoretical frameworks. It would challenge our understanding of quark confinement, the forces that bind quarks together, and the stability of nuclear matter itself. We would need to explore new equations of state for extreme densities, potentially unlocking secrets about the early universe and the conditions under which matter first coalesced. The very definition of a neutron star, the densest known objects besides black holes, could be rewritten if they were, in fact, colossal lumps of strange matter, strangelets. This realization would transform these cosmic titans from mere remnants of stellar collapse into cosmic laboratories, offering tangible, albeit immensely challenging, avenues for direct observation and verification of this exotic state. Furthermore, the quest to comprehend the universe's most enigmatic constituents would gain an entirely new dimension. For decades, scientists have been peering into the cosmic abyss, analyzing the faint whispers of radiation and the energetic signatures of distant celestial events. The ongoing quest to understand the universe's most enigmatic constituents, from dark matter to the fundamental forces, would be invigorated by the concrete possibility of finding and studying strange matter. It would provide a tangible target for our observational instruments, a new frontier to explore with unprecedented rigor. The subtle signatures of strangelets, perhaps interacting with ordinary matter or leaving their unique imprint on cosmic rays, would become the focus of intense scrutiny. This pursuit would not only deepen our knowledge of the cosmos, but also inspire a new generation of physicists and astronomers, pushing the boundaries of human ingenuity in the pursuit of ultimate cosmic truths. The universe, it seems, still holds secrets far stranger and more profound than we can currently imagine, and the allure of unlocking the paradox of the alchemist's dream, turning the familiar into the fundamentally new, continues to drive our relentless exploration.